Okay, we'll wait for the students for about 5 minutes so that they can join the class. I'll turn off my video for a while. Okay, uh, I think we'll start now, even if there's no one present. Mm, Let me share my screen. Okay. So this week, the videos were about elastic theory. Uh, we'll not go into fluid mechanics, only the elastic theory part. These were, I think, lecture, it's the fourth week, so in 13 to 16. In the first lecture, we learned about, we defined what stress is, what body forces are, stress body forces, uh, and then we define strain, and yeah, and then we define strain, and we also define We also defined relation between stress and body forces, which is this equation. Some kind of continuity equation. This is a vector equation, by the way, because sigma is tensor. Yeah, that is too soft. And we also saw uh, the definition of Young's modulus, Poisson ratio, and the stress strain relationship. The stress strain relationship, stress strain relationship is the relation epsilon ij, which is the strain matrix, is equal to 1 plus mu by epsilon, sorry, E times sigma ij minus mu by E sigma delta ij, where sigma is equal to sum over I 1, 2, 3, that is 3 dimensions, sigma I. Mu is the Poisson ratio, and E is Young's modulus. Then we studied a method called stress function method, which is just using this equation to solve for strain, this equation and the stress strain relationship, to solve for epsilon ij uh, or sigma sometimes, depends on how the problem is. After that, we studied some examples of the strain functional method, and then lastly we studied about the strain energy, which is the elastic energy stored in any material at any point is given as half strain some matrix which obeys Hooke's law, then again strain minus trace of this epsilon x times v of x, where v of x is the potential responsible for body forces. That is, x is equal to minus del v. This was all that was in this module. And now let us start from the starting, which is the starting these things. So Yeah. So first hmm, thing is, we want to define stress, and you have a closed body. You have a closed body, and uh, as I said, that stress is a tensor, and uh, you want to find. So, what is the question is, what is the, so suppose there is a closed body and there is a stress tensor, sigma ij. Now you want to find and consider the unit to the surface as normal to the surface as n cap. What is the stress which is being applied on the whole of the body, whole of this closed object? That is the first question. This is given as is equal to, suppose this S denotes the surface, and dF is a small force which is acting on the surface. Suppose some dF is acting here. So that will be written as dF is nothing but dot sigma ijx times dA. So stress can be thought of as uh, force times what stress can be thought of as some kind of a pressure, pressure times area in along that direction, along the normal direction, and you integrate over all of the uh, all of the uh, all of the surface of the object in which you are interested in, and you will get the total stress. And this is equal to this. So this is the answer. Now, suppose this, suppose a body force is also being applied here, and the body force is applied in such a way that is the uh, in such a way that, so stress is something which is applied by outside. Now, if the material is not deforming, that means there is something, some force on the body which is not letting it to be deformed, right? So this body force is the, so this body force at any unit, like body force per unit volume, if it is given by PV, what is the net body force over the whole surface? That is the question. And it is just integral over dV, uh, and V is the volume which is enclosed by the surface times FB, and this depends on your position. And if the body is not deforming, or if nothing is happening to the body, then this force should be equal, this body force all over the surface should be equal to the negative of the stress which is being applied from outside. So that is the idea. Now the third question is derive dot sigma plus x equal to 0 from this equation. This can be done as follows. You take this equation, And you can write the stress as from equation from this equation one. Now use the divergence theorem to get such a term. Now argue that since this is true for any volume, it is true for any arbitrary volume. So this should imply that the integrand is 0. So that is how we prove this relation. A thing to note here is that this is a vector, so this also should be a vector. But divergence just takes one of the index out. Okay, let's go to problem 4. So if we want to know what the stress is, given the body forces, we need to solve this equation, and we need to solve it in such a way, solve it with the appropriate boundary conditions. Generally, the boundary conditions are that this term, the stress uh, in the boundary of the surface, should be equal to the, what do you say, uh, should be equal to some normal to the surface, should be equal to the stress which is being applied there. Say stress, which is some stress or some surface force which is being applied, whatever it may be. Okay, good. Now let's do some problems on strain. So strain is a in 3 dimensions, strain would be a 3x3 matrix, and this can be written as some A sigma ij. Strain is the response of the stress. So we are relating strain by such a way, and look that this is the relation is linear. So this relation is only applicable to materials which are linearly deformable. This just means that the equation between the strain relation should be linear in relationship. Plus B sigma delta I comma j. The reason for writing this in this way is because the trace of uh, the trace of the sigma ij, which is nothing but this thing, is an important quantity. This is similar to pressure, and when ij are not equal, ij are not equal, this is mostly shearing stress. That is why we want to write this term differently from this term, because we want to see their effects differently. All of this, when I not equal to j, constitute the uh, shearing stress, and when I equal to j, it's just the pressure. So now our question is to argue that A is 1 plus mu by E and B is equal to minus A by E, where mu is Poisson ratio and E is Young's modulus. So the way to do it is that we'll assume that all other stress except in the x direction is non-zero. So there is sigma xx, so this is non-zero. All others are zero. Sigma yy equal to sigma zz equal to zero. Then we'll have epsilon xx equal to A sigma xx plus B sigma xx. That is equal to A plus B sigma xx. The Young's modulus is defined as if you are applying stress along a direction, say x, and if you are finding the strain in that direction itself, say the stress is denoted by sigma x, sigma xx, and the strain is given by 7xx. Then the Young's modulus says that the strain in the same direction divided by uh, sorry, the stress in the same direction divided by elongation in the same direction, the strain in the same direction. This ratio is defined to be the Young's modulus. Now, yeah. So EXX is this. So this is the definition. So from the earlier relation, from this relation, we get that E is equal to 1 by A plus B, or A plus B equals 1 by E. And and yeah, and now let us check what happens in the other direction. For example, EYY. For EYY, we have A sigma YY plus B. Uh, since this is the trace, we have sigma XX plus sigma YY plus sigma ZZ. So delta YY is 1. Since sigma YY and sigma ZZ is 0, we have this as this. Similarly, this B sigma XX. We define the strain in the other perpendicular directions, perpendicular to the direction where we have put the stress, the ratio of those strain as the Poisson ratio with a negative sign. So by is the Poisson ratio. Now, what we will do is we will, yeah. Oh, this is sorry. This should have been stated from the strain in one of the perpendicular directions to the original strain. This is defined to be the Poisson ratio. So from here we'll find B sigma xx by epsilon xx is epsilon xx is just this a plus b sigma xx. This is equal to minus b by a plus b. So and a plus b is just e. So we will get mu is equal to minus be. Therefore, b is equal to minus mu by e. 1. And a plus b is equal to 1 by e. This implies a is equal to 1 plus mu by e. Therefore, taking this example, uh, taking such a case, we can substitute in the original epsilon ij, and we get sigma ij minus mu by epsilon sigma delta ij. So yeah, so that's what we have got. Now we are going to do some problems in uh, stress function method. So the stress function method starts with the idea. Uh, just 1 second, I'll just print some more. Okay, now we'll do some problems in stress function method. So the uh, stress function method uses the extensive use of the equation, this equation, A okay, plus B okay, body force in the j direction is equal to 0. Now we are going to assume that body force in the j direction, the body force can be written as the gradient of some potential. Yeah. Okay. So therefore this equation becomes now you get different equations for different relations. Uh, for example, say choose j to be x, then you will get del x sigma xx plus del y sigma yx uh, minus del x d of x is equal to 0. The x here is all x comma y. Suppose this is two-dimensional. Suppose this is a two-dimensional system. Example, 2D. You get this, and you are going to find another equation when you choose j equal to y. Yx plus, uh, oh sorry, so j is y del del y del del x of xy del del y y is equal to del del y fx. Now we are going to find what is the strain if the potential given is say v of x is question v of xy, say it's a three-dimensional material, is equal to rho gy. What is the equations? Then we are going to have del I sigma ij is equal to del j v. Now v only has y, so uh, we'll have del I sigma ix equal to del I sigma iy I iz. Okay, let us take only two dimensions for the sake of simplicity. So this is equal to 0, and sigma I and del I sigma I y is equal to del del y rho gy. Is just okay. Therefore, del x rho xx plus del del y rho yx is equal to 0, and del del x rho xy plus del del y rho yy is equal to rho j. Now we know xy equal to uh, yx. Can we do something there? How do we solve this? There are two equations and three unknowns. Uh-huh. Very small plus. Um, these are going to be the equations. We can't solve it exclusively. Okay, we can do one more thing. I'll differentiate this by del del x, and I'll get del square sigma xx plus, and I'll differentiate this with del del y, and I'll get is equal to 0. Now this and this term is the same as sigma yx is equal to sigma xy, and we can subtract it to get del square sigma xx square is equal to del square No, hmm. This is based on this assumption, which is mostly true. Now, what you're going to do is going to argue that since this is only a function of uh, no, this argument may not work. Yeah, that is what you will reach. So if we say that sigma xx is only a function of x, since this part is only a function of x, and this part is only a function of y, uh, if we say that this is a function of x and this is a function of y, then we can solve further. So function of x is equal to function of y. That means it should be a constant assumption. Well, we can leave it here. It's all right. We'll do some more problems. Okay. Hmm. Okay, now what you're going to do is question verify that sigma xx. This is the same thing. I'm dropping the arguments. That is, I'm dropping y, xy in the bracket. Satisfy these equations. So in other words, what I have done is just that I have backtracked, but we can directly verify also. Now, first equation is ddx sigma xx plus y y minus sigma y x is equal to I substitute just now. I get dv by dx plus d square d, d cube dx dy square phi sigma y plus del y of sigma yx which is equal to sigma xy is just minus of del cube phi del x del y square. Hence you get dy by dx. Similarly, you'll get the same thing with this also. Y plus del y, y, We will give you dy. Okay. So we are done with this problem. Now we will show that the most general strain, which is given as so equal to delta ux. Ux is the displacement along x direction from the when the stress has occurred. This is the small du is the small displacement along x direction, and it is a function of all the other coordinates also. Similarly, ui is along y direction, but it is a function of all the other coordinates also. And epsilon xy is equal to half del x del y del u y. Now we will verify. Uh, now we will verify the equation. Verify this is called the compatibility condition. Hmm. So let us verify that LHS equals del square del square epsilon xh. So that is just del ux del x del square del x square del uy del y is equal to del square del cube del y square x minus del cube. And yes, you get this. Let's look at RHS, which is 2 times del square. Now it's going to become as half and half. 2 gets cancelled. Del square del x del y del ux del y plus dy. And these two match. And so we verified the compatibility condition. Now what we want to do is let us solve for stress and strain in the case of plane strain. So, yeah, so the idea is, yeah, so the idea is, okay, question, find the compatibility condition for a plane strain. So, in this situation, that is epsilon zz equal to 0, for example. This is a thing. So the way to find is ezz is equal to 0. And now we know what this ezz is. It's nothing but E sigma zz minus mu by E sigma xx plus sigma yy sigma zz delta zz, which is equal to 0. Now this term and this term, they vanish. So it is just z is equal to mu by E sigma xx plus sigma yy. So we know that the stress in the z direction, zz direction is related in such a way that, okay, this was cancelled. Now we'll put this in the compatibility condition. Okay, we got sigma zz. Now, yeah, we need to find sigma xx to put it in the compatibility condition, which is this. We need yy and xy, and xy. Yeah. So now we want. Yes, yes. Okay, let's find that. 7, 7, x is equal to 1 plus mu by x e sigma xx minus mu by e sigma xx plus. Now this is equal to. So we'll write this in sigma. We will try to eliminate the z from mu by e. We substitute for this, so we just get 1 plus mu sigma xx plus sigma y. Sigma xx equals 1 plus mu by e 1 plus mu by e. Uh, take that as common. Sigma x is taken as common, and we'll get 1 minus mu minus a mu by epsilon 1 plus mu sigma y. This is nothing but 1 by e sigma xx n minus mu square minus mu plus mu Uh, so this is the thing. Now we'll find yeah, this is correct, and we'll find sigma epsilon yy. Similarly, uh, we'll have everything to be the same, but xx and yy will be changed. So we'll get 1 by e sigma yy minus mu square mu plus mu. This can be easily seen from the calculation. It's just we'll be putting yy here, and the rest of it is unchanged. So since there's no difference between xx and yy, so it should just be this epsilon xy. We'll find this now. Epsilon xy, we have uh, 1 plus mu by e times sigma xy minus, we'll have a delta xy term here, and since this is 0, we'll just have this part. So this is equal to 1 plus mu by epsilon sigma xy, just this. Now we are going to substitute this, and we get 2y gives this equation. By e, and xy is equals mu square dx so we can cancel this by e. We get 1 minus mu, and we'll take this to be common. Del square dy square sigma xx plus del square dx square sigma y minus mu del square del square sigma y. Yes, 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 yes. Sorry, this is excess there. Is equal to 2 times del square LX by Y sigma x. Now, what we want to do is we want to eliminate those XY terms. That is, we don't want any sharing stress. We want to have only the normal stress in this condition. That is XX and XX, sigma XX, sigma YY, all these terms. So, what we will do is we will just verify an identity. It goes as like this. Now we know that we know from the the condition, from this condition, where are the equations? Yeah, we know from these conditions we have a relation between the potentials and sigmas. We try to substitute sigmas from this thing. So, so this is main equation. And it is now we will try eliminating sigma x y. So what we will do is we just copy this equation. Um, okay, and then what we will do is uh, we will differentiate this with respect to x. So we'll find here this, this. We'll differentiate this with respect to y. Find here this, this, this. Now we will add this equation. Add alpha with beta. And we will try to separate the part which has got this term. And then we will substitute this in A. So we have 1 minus u del square sigma xx y square plus del square del x square sigma yy minus nu del square sigma yy del square is del square sigma xx del x square is equal to del square del x square del square del y square. Plus del square del y square sigma y1. So we see we get a term. We uh, you get a 1 minus u term if we club this term and this term together, and 1 minus u will take it outside. You will get. So this is the equation which we are going to get. And this can be written as uh, yeah, this can be written as this can be factorized very neatly to write something like this. And then assume there are four terms, so we want four terms. So this is common here and here, and we can write this as this. Check that this gives you all the terms. This term is there, this term is there, this one, this term is there, and this term is there. And we are done with it. Now we can so we wrote the general function which applies to this thing, right? So we can just use that and substitute this here in sigma x and sigma y. This is the potential. Similarly, y is the same. And after substituting, we will get minus v a square a square. Two times v is five v square. So we have this. This is u. This is v. And I think I forgot the name somewhere. No, it's not here. So we will get v minus v. So yeah, we will put this term together and we'll put this term with this. So we will get 1 minus u del square del y square plus del square del x square square. That means this operator is again here 5 is equal to, we will put this term this side, and we have 2 minus nu, that is 2 minus 2 nu here, 2 minus 2 nu, and it comes this side, and it will be 1 minus 2 minus 2 nu of this term only, which will give you, and this will give you, this is just 1 minus 2, yes, this is 2 nu minus 1. So we'll get the equation, final equation of 1 minus nu del square del x square del square del x square square 5 is equal to 2 minus 1 del square del x square del square del x square b. Done. This is it. So if b is constant or 0, or b is a linear function, c1x plus c2y, then our equation is just del square del y square plus del square del x square square phi is equal to 0. This means that mm, so phi at most can be, uh, phi can at most be, so so phi will at most be uh, cubic in this case, right? Okay, for an example, this is a problem question. Okay, this is, yeah, we're done. Now question. Suppose phi is equal to minus f by d cube x square 3d minus 2y. So clearly body forces should be absent, and now we'll find, so we can directly find what the stresses are and what the force acting on. Uh, so find sigma and at the surface. So I'm so sorry. Let me just be back in a minute. Okay, so we know how to find sigma xx, uh, v0. So we have del square phi del square is equal to del square del square 3b square minus 2x into 3b to 6 dx minus 3 to the 6 y square 6 to the 4 x sigma y is equal to y square the x square 5 y square the x square is equal to dq 2 dx y square minus 2x y cube to 0. Sigma xy is equal to the square x square y 5 is equal to, let me take the first derivative of x here. So x y square, so it will be y square, and this is nothing but x and d cube equal to 36 d minus 6 x square. It's not x square. Therefore, f uh, at the surface expressed is normal to surface normal dot sigma and the surface the line So let me just write what n dot n sigma is. So that is, we have sigma xx, which is non-zero, and sigma xy, which is non-zero. Sigma xx, x cap, is sigma xy, y cap. This would have been force in the x direction actually if we do the integral, but leave it, it doesn't matter. So we'll look this at y equal to 0, y equal to 0, y equal to 0, we have minus x d cubed 6dx. Okay, we'll look at a surface. We'll look at this surface. So we'll look at the surface. See, this is my XYZ plane. We look in the XZ plane. That is y equal to 0. Or if it is a two-dimensional surface, we'll look it into this in this line, which is y equal to 0. So n cap dot sigma at y equal to 0 is equal to sigma xy y cap j cap plus sigma xx x cap. So this is along the x direction. So this will give us this will give us the sigma xy at y equal to 0 gives us xy cube 6d j cap plus sigma xs x at y equal to 0 gives us minus d cube 6d x. We've taken the dot product, right? This is the dot product. First, we can, so y at y equal to 0, we have this is 0, this is 0, sigma xx is non-zero, sigma y is 0. And this is this thing. If you want to find the total between some length minus L and L, and in the z direction as such, you will have to integrate over that area. And it's as simple as it is. Let us go to another question and let us do this problem. So the problem is as follows. We have a cuboid of side Lx, Ly, Lz, and it is made of some elastic material. The body force is given as minus mg by v t cap, where v is equal to Lx, Ly, Lz, which is just the volume of the cuboid. Now, from the equation, okay, so what we need to find here is all the stresses, all the strains, and then all the stress and all the strain, and also, yeah, that's all. We need to find here all the stress and all the strain. Hmm. Let us do this slowly. Let us do this example properly. So the first thing to use here is the equation, which is nothing but this equation is equal to FD. Now, since this is in K, this thing, since this is in the K cap direction, uh, so this J is the Z direction. So I have del X sigma X Z plus del Y sigma Y Z plus del Z sigma Z Z is equal to mg by d K cap. This is one. The other equations when J is equal to this is equal to this is for J is equal to Z. Now we'll take J is equal to X and Y. So we'll have del X sigma XX plus del Y sigma YX plus del Z sigma Z 0 del X sigma X Y plus Ly sigma yy to 0. These are the two equations, 2 and 3. Now, what we're going to do is, yeah, at this stage, so so we are also going to assume that the component of the stress on the bottom surface, that is n cap equals minus k, is nothing but sigma zz of minus k. Should be the force acting on the bottom surface per unit area. So this is like mg by Lx Ly. Is understandable. So we find that sigma zz. Now you see the body force is applied in the k-cup direction. There is no shear here. We are not shearing it. So if this is the material, the cube, x, y, z, x, y, z, we are pushing it. We are, the body force has been applied negative to the force which is being applied on it, like say So the force applied is something like this. So the negative force, it's somebody is pulling the material on the top face, and the body force is like pulling it inside. It does not want the material to disintegrate. Then there won't be any shear component. So with this logic, sigma ij is equal to 0 for I not equal to 0. From this intuition, we have this thing, we have this argument. This simplifies our equation very much. So as we'll have only this equation. Which implies sigma zz is nothing but mg by d z plus some constant which we need to figure out. So, z is a constant in x. It can be a function of x. So this is one. Similarly, we have uh, we have the other things as other equations from other equations. Sigma xx is equal to function of yz, function of yz, and sigma yy is equal to some other function of xz. These are the other equations. Now we have been assuming the force is uniform at z equal to 0, if z equal to 0, suppose it is a uniform force, then at z equal to 0, you are going to get cx comma y. And suppose this is mg by lx. Okay, so the material is, say, it's only till here. Say it's a cylinder and it is only till z equal to 0. And the body force is the force which is being applied everywhere. It is even applied on the top face, even on the bottom face. So the body force, like this is same for all over the material, right? So the body force in this part, the bottom part would be uh, body force times body force is per unit volume, and we want this thing stress is per unit area. So Lz, which is the which is the um, volume in this, which is the area in this thing, and times Lz. It's like force by area. So what I want to say is this is force and the area is Lx times Ly. Lx Ly times Lx times Ly. So force per unit area. So body force divided by the Lz. So Lz length. So this we are writing this because body force is uniform over the surface of the material. Now, given this, you can write this thing as sigma z z Eg by Lx Ly Z minus, so Z V has a LZ, so Z by L1 minus 1 plus some C prime of XY. Now we are going to say some symmetry argument, and we can argue that this is equal to 0. The reason is that the cube looks symmetric and the body force is also symmetric. It is all straight, it is all in this direction at the top surface and in this direction at the bottom surface. Now, there is no, uh, so this sigma zz, if it constitutes, if it means, if it is meaning that it is stress in the z direction, it is not affecting, it is not affecting the, it is not being affected by the other direction as per the problem. Thus, we just have this. This is something which is again intuition based. Even if we rotate the cuboid, the force is going to look the same. So, by that argument, C should be rotationally invariant. Even if we translate, go above and down, this function should not change. The function in the xy direction should not change. Z direction it will obviously. So C should be translationally invariant also. The most common, like the function which will satisfy these both of these things is that C prime is equal to 0, because that means that if it is a cuboid here, what I mean to say is if I take any plane here, so this is my equation. Uh, so any point here, any point here has the, any point in this plane has the same stress. That means the stress only depends on the where the plane is located in the z-axis, not on x or y. Okay. So that is why this is 0. So yeah, now we will calculate. We got sigma zz. Now we'll find the strain. The strain in the x direction is the same as the y direction because of the symmetry of the problem again. This is 1 plus v by e. Okay, let me just write the stress strain relation. So it's equal to 1 plus mu by e sigma xx minus by e sigma. Mhm, delta xx, delta xx. So this is equal to sigma xx minus. Now the stress is only in this direction. Sorry. There's one more thing. There's other direction stresses. But the same argument which I just made. The stress in the other direction they're also zero. The reason is because is a function of stress in the x direction is a function of y and z. Should be a function of y and z. But stress in this direction, in the x direction, is zero because the body force is being applied only in the z direction by the body. That means the stress which has been applied by someone in the like outside of the material. If somebody is applying stress onto the material, it's being applied only on the z direction. Because of that, the body force is opposing it. So the stress in the x direction or the y direction is also zero. Therefore, now we can find sigma xx is equal to 1 plus mu by e sigma xx minus mu by e sigma. Now sigma, the non-zero component is just zz. That implies this is also zero because this is zero. So sigma epsilon zz epsilon xx. Similarly with epsilon yy is minus mu by e sigma zz plus 10. And epsilon zz will be this mu by e sigma zz minus mu by e sigma zz. This gets cancelled. This is just sigma zz by e. Therefore, we can find the displacement. So this is the strain. Strain in the xy is zero. Now we can find, say, xx is nothing but the displacement in the x derivative of displacement, the partial derivative. And we have epsilon to the is equal to minus mu by e sigma zz. And sigma zz is not a function of is a constant function in x. So ux of x, y, z is just times x plus c. Okay, with this constant now if this is a this can be a function of z. So I'll write this cx and is equal to minus mu by e sigma zz is what was it? Sigma zz is mg by lx ly z by z minus 1. dy xyz because dux is in And Z is epsilon ZZ, which is sigma ZZ by epsilon. So we need to do this properly. It is only we can't dz. So dz by dz is epsilon ZZ. This is equal to sigma ZZ by E. And sigma ZZ, as we know, mg by Lx and E, z by Az minus 1 minus u1 x z is equal to mg by E Lx by Y x squared by P z minus z is Cz. So, so this is what is there. Yeah. Now we want to find what those constraints are, right? The way to find those constraints are by looking at define Cx, Cs, Cz, these the equations Pij equal to 0 for I not equal to G. So let us take a epsilon xy is equal to half du Vcx dy plus. Okay, this is one. This is equal to 0 is 1. Dy will give us Dy will give us this we need to be a bit careful. U x duy duy implies duy by dz is equal to is equal to this is what we need to use. It is minus mu by e u by x over z is y plus dp plus del del y. Z is respect to u just c1 is it. Now uy z and ex z equal to half the u x is z u y is equal to 0. This implies ux. Similarly, ux also has a similar term minus mu by e and dx dx plus del del z cx plus del del x cz is equal to 0. These are the three equations which you are going to get. So now we have to argue from here, and the way to argue is from the first equation. Now Cx is a function of y and z. Cy is a function of x and z. And it is giving this thing is giving to be 0. So either Cx is a constant function of y and Cy is a constant function of x. In that case, we can satisfy this. Or we may have Cx to be a linear function such that dCx by dy is a linear function of is some constant, and this constant cancels with the constant which comes from dcy by dx. So that is one thing which we can argue. So let's see what can we do. Hmm. So the best possible way is to look at A and argue. So in A, which is the equation del y Cx, xz, Cx, yz, double x, Cx, xz is equal to 0. What is the most general C which will satisfy this? Let me do this to be some f of y, g of z, and cy to be, let me do this as a separation of variables. Fy, f1, g1, fx, gx, fy, x, g1, okay, this is very confusing. Cx is written as f1, g1, cy is written as f2, g2. And we'll find the conditions. So del y will be acted on only f1. So we'll have g1 of z del y f1 f1. Plus similarly we have g2 of z del f2 del x. This should be 0. This implies this can happen. Yeah, this has to be 0. This can happen if this can happen in a lot of ways. Let's see. Now, since this is a constant, we can always put some function alpha of z plus beta of z. And the reason for doing this is it also satisfies this equation. So this is the most general CXCY. Now, what we are going to put some condition in this is that if one of y is equal to y, to x is equal to minus x. We could have and g1 z g1 equal to g2. Now, we could have taken something like g1 equal to minus g2 and f2 of x is equal to plus x and f1 of y is equal to y. But up to science, I think up to science, this is the most general uh, equation that can be. Therefore, if we use this, we have Cx is equal to y g1z plus alpha z and Cy is equal to minus x g2z beta z. Now we'll put this in B. But yeah, Hmm. Well, yeah, one should be subtle while adding the boundary condition. Okay, uh, what one can do is, so this is YZ, this is XZ. Now, we can put this thing to be, yeah, we'll put this thing in B and C. That is the first thing to do. In B, if we put this in B, we have minus mu by E n g y x a y x a y and z y plus del cy by del z del cy del cy by del z del cy by del z. And we are going to get minus mu by E g y by x a y l z plus del del z cy is equal to mm, x2 x, which is minus x plus minus x del gt del z del beta del z plus cz del y. Yes, is cz is just cz. So we have we can differentiate the equation once again with respect to y. And if we do that, we'll find that this term goes to zero, and this is just a constant. But I don't think it's very useful. Okay, anyways, this is a function of g2 is a function of z, beta is a function of z, and this is y. So cz should be equal to minus mu by e in g s squared by 2 lx over lz, okay, plus sign, plus sign. Then only if we differentiate, we will get this to be 0, and plus And CZ can't be a function of CZ can only be a function of y and x. So x plus some function of g of y comma x. So this implies that minus x del g2 del z that plus beta del z z plus del g is equal to 0. Now we have to solve this equation. It is a bit tedious, but yeah, I'll present the solution in next class and we'll be done with this. Or we may take any other assumptions and solve too. This is getting a bit tedious, so we'll leave it at this only. So with this, I end my class. Uh, class dismissed.